two more.
Okay.
All right, so two more questions. What does Thevenin's theorem say? Give me the essence of Thevenin's theorem. Anybody want to try it? You can come up here and use the board to do it. William, you don't want to?
Say it.
Yes.
A voltage source with a resistor in series has an equivalence circuit, which is a current source with a parallel resistor.
Okay, that's what you said is true. That's not quite Thevenin's theorem, but it is true what you said. If I heard you right, you said that a voltage source in series with a resistor is equivalent to a current source in parallel with a resistor. And that is absolutely true, as long as the resistors have the same value, right? And the relationship between the current from this source and the voltage at this source basically looks like Ohm's law. It's got to look like this. So, and I have a subscript there, T, which stands for Thevenin. So if the relationship between the V and the I follows this, and the R's are the same, then yes, these are equivalent. That's not exactly what Thevenin's theorem says, though. What Thevenin's theorem says is that, I'm going to label these terminals A and B. If you have a network that has two terminals coming out of it, A and B, and the network, you know, it could be anything. Any complicated circuit with resistors in parallel, series, you could have dependent sources, independent current sources. It could be really complicated. And you look at it and you think, oh my God, I don't want to deal with this. Here's what Thevenin says. Thevenin says you don't have to deal with this because this complicated network is equivalent to this. So that's what Thevenin's theorem said, where you have some voltage source in series with a resistor. Now, the problem is, of course, what's the value of that resistor and what's the value of the voltage source there? And of course, there's a whole procedure for figuring that out. But essentially, this is what Thevenin's theorem says. And so you have that big picture. Similarly, we've got something called Norton's theorem that says pretty much the exact same thing, except that instead of the equivalent circuit being a voltage source in series with a resistor, we've got a current source in parallel with a resistor. But we could do that by what William said. And by the way, what William said is called a source transformation. You know, you can have a voltage source in series with a resistor and transform it to a current source in parallel with the resistor. By the way, who knows the name of this thing? This, just the voltage source here, that's an ideal voltage source. That's an ideal voltage source. But when I put it in in series with a resistor, the whole unit, this whole thing, has a name. And it is called, anyone know? No. Well, this is called, you could call it a Thevenin equivalent circuit. And I would have to give you full credit for that answer. But what I'm fishing for, this is a practical voltage source. Do you remember reading about that? Yeah, so this is an ideal voltage source, but if you actually look at, if you looked at the terminals A and B and you really didn't care what this was, just think about it as a blob, the voltage current characteristic, in other words, the relationship between the voltage and the current, is much closer to what really happens with an actual voltage source in the lab than what happens with an ideal voltage source. Because really, if we were to plot the voltage of an ideal voltage source versus the current, it would just look like that, right? It's a constant because we said it's independent of the current. That's our definition of an ideal source. Well, you know, real sources don't act like that. If you go into the lab and you measure the voltage coming from that source, it does depend on the current. And so This, if we actually were to plot it together with the resistor in series, it would look more like that, which is still not what the actual voltage source in our labs look like, but it's much closer. It's a better model. So we call it so this, that now I erased, is called a practical voltage source. And then the ideal current source in parallel with the resistor is called a practical current source. Okay, and then finally the last question. What's the advantage of using nodal analysis or mesh analysis to find a current or a voltage in the circuit rather than just applying Kirchhoff's voltage laws or Kirchhoff's current laws by, just on your own, instead of following the procedure of the node voltage or mesh current analysis? Think about that while I erase. Anyone? It's a long question, but the answer's short. Let me repeat the question. What's the advantage of using the node voltage analysis or the mesh current analysis rather than just, doing it on your own? Just, looking at the circuit and applying Kirchhoff's voltage laws or Kirchhoff's current laws.
Last equation.
What?
Last equation.
Last equation? What do you mean by last equation?
More efficient.
It's more efficient. It's more efficient. Why is it more efficient? Because if you follow the procedure, you're guaranteed an answer. You are guaranteed an answer. If you just go on randomly, apply Kirchhoff's current law or voltage law at various points in the circuit, around a loop or a mesh or a node here or a node there, you'll have some equations that might get you an answer, but you're just going to have to pray to the gods of circuits to, guarantee it. If you follow the steps of node voltage analysis or mesh current analysis, you're guaranteed it. You just follow the steps, you're going to end up with n equations in n unknowns, and you're going to get an answer. So it's efficient because you're not going to waste your time. So really, I want to make sure that everybody can apply these steps. So I have a problem here that we're going to work on. I was going to say something else. What was it? Anyway, any questions about anything so far? All right. Okay, so I have a problem on the board here, and basically what you're asked to find, and this is actually a difficult problem. I don't know that I would put this on the midterm, but we're reviewing, so, so no. All right. But if I did have something this hard on the midterm, you would breathe, and you would just tell yourself, I can do it, because I'm just going to follow the steps, and I'm guaranteed an answer. So so don't panic. What's that thing? Keep calm and follow the steps of node voltage analysis. Okay, so here's the given circuit. It looks like a scary looking thing. We've got a voltage-controlled voltage source, right? And we've got a current-controlled current source. The current that controls this is here. And the voltage that controls this is here. So, okay, so it's kind of a scary looking circuit. It actually happens to be, what is it? Some kind of transistor. It's an equivalent circuit for a transistor amplifier. Anyway, I don't care. I'm asked to find the maximum power that can be delivered to a load at the terminals A and B. Okay, so there are some things that you're expected to know. So in the solution, okay, and by the way, and I'll put this in the weekly email that I'll send this afternoon, but on the test, you are expected to follow the standard format for, engineering problems. So you have to have in your section all the given information, and then clearly identify what it is that you're being asked to find. And then when you start your solution, I want the solution to be very clear and show me every step you're taking and why. So, for instance, here we're being asked for the maximum power that can be delivered. Well, I'm hoping that ringing a bell for you, and it's bringing to mind the maximum power transfer theorem, which says, what does the maximum power transfer theorem say? What? Okay. You remember the formula, but I want it in English. Okay, he said v squared over 4r. Whoa, well, what's the v and what's the r? You get partial credit. Okay, what the v and the r is this. The maximum power transfer theorem says that the maximum power will be delivered if the resistance of the load is equal to the Thevenin equivalent resistance of the circuit. And the power, the maximum power, will be equal to v squared over 4r, where r is the Thevenin resistance, and v is the, oh, I know what it was earlier. I was going to explain the subscript OC. V is the voltage of that Thevenin equivalent voltage. Okay.